Hey everyone. So today is another day of practicing linear approximation. So last lesson we talked about the idea of what a linear approximation is, and that is exactly a tangent line. So remember, a linear approximation is using the equation of a tangent line to estimate the values of a function that we can't normally determine without a calculator, okay? So remember, the word linearization is just another word for tangent line. And today we're going to be looking at the idea of concavity, and we kind of introduced that idea last time, but we're going to formalize it a little bit more here so we can see it a little bit better, okay, to determine whether the approximation is over or under the actual value, okay? So here's the statement. If a function is concave down, then the linear approximation is an overestimate. So we can see that. If I were to graph a concave down function, something like this, concave down, we can see that no matter where I put a tangent line, if I put a tangent line at that point, or if I put a tangent line at this point, no matter where I put that tangent line, the tangent line will always lie above that function because that function is concave down. Well, conversely, we would say that if the function is concave up, if the function, well, let me see what's going on here. Let me back up. If the function is concave up, something like this, you can see that no matter where you put the tangent line on this function, the tangent line will always be below the actual value. And so remember, our goal was to figure out, let's say, what this value is of that function. Let's call that, like I did there, let's call that, I don't know, let's call that D. And then this point will be C, okay? So we're finding the equation of the tangent line at C in order to estimate the value of the function when x equals D. And so we have to look at the value of the tangent line at D and say that the value of the function is approximately the value of the tangent line. The question is whether it's going to be an overestimate or an underestimate. Well, in this case, we can see that the tangent line is above, so we can see that our estimation on our tangent line is above the actual value of the function. And the reason it's above is based on its concavity. So now let's get into what I was going to say here. Basically, in notation form, this is the equation of the tangent line. So remember, L of x represents the linearization or the tangent line. And so this is in point slope form. Y of our tangent line minus the y value of our point of tangency, f of c, is equal to f prime of c, which is the derivative, the slope at that point, times x minus the x value of that point. So it's just y minus y1 equals m times x minus x1. And then, of course, we would isolate L of x so that we have our linearization. And so if we had numbers or functions to work with, we could simplify this. But this is the general form or the basic form of a linearization. L of x is equal to the slope times x minus c plus f of c. That's the point slope form ultimately. But now we can say if I wanted to estimate L of d, this point that is, if I want to find f of d, if I want to find f of d, I'm going to use L of d to approximate it. So we'll plug d into our linearization, and we would say that L of d is whatever this is, so therefore f of d is approximately that. So you can see f of d, the yellow writing there is not very clear, but that's okay. So we can say since f double prime of x is less than 0, right? Since f double prime of x is less than 0, we can say that f is concave down. And as a result of that, we can say that our linearization is greater than our actual function's value. And therefore, we end up with an overestimate, okay? So that's kind of the idea behind concavity and linearization, okay? And of course, we can go the other way with that. Of course, if we have our function opening up, we would have f double prime of x is greater than 0, which is concave up, which implies f is concave up, and therefore the linearization would be less than the actual function's value, and therefore it's an underestimate. So let's go ahead and do a practice problem dealing with this. Let's say that f of x is equal to the natural log of x plus 1, and we want to find the linearization of f of x when x equals 0 to estimate the natural log of 1.1. So let's go ahead and find the linearization of that first. And the way we do that is we find the point and the slope. So I'm going to go ahead and find the point first. So f of x is equal to the natural log of x plus 1. So I want to find the point. So the point is going to be plugging in 0. So f of 0 will be the natural log of 0 plus 1. Well, oops. That would be the natural log of 1, which is 0. E raised to what power is 1? That would be 0. So our coordinates for our point of tangency is 0, 0. Okay? Then we need to find the slope. So to find the slope, we need to take the derivative. So that would be 1 over x plus 1 times 1, chain rule, because the derivative of x plus 1 is 1. And then we need to plug in our point of tangency. So f prime of 0 is going to be 1 over 0 plus 1. So that implies that f prime of 0 is just 1. So then if I'm going to create my tangent line or my linearization, we would say y minus 0 equals 1 times x minus 0, right? Because our coordinate was 0, 0, and our slope was 1. And of course, we want to write that as a linearization, so we say L of x instead of y. So we could say L of x minus 0, but I'm just going to put L of x. And then simplifying this side, it just becomes x. So this is our linearization. And now we want to use that to estimate natural log of 1.1. Now, normally, we would want to plug in 1.1 back into our linearization, but you have to pay attention to the function that's given. The function is the natural log of something plus 1. So you have to think, how do I get natural log of 1.1 out of this function? So we would say something like this. We would say the natural log of 1.1 is equivalent to f of x when x equals what? When x equals 0.1. Because f of 0.1 would give us the natural log of 1.1. So since we are looking for when x equals 0.1, that would produce f of 0.1, which would be natural log of 1.1. So you have to be kind of careful of that. You don't want to just plug in 1.1 because that's what we're looking for here. You have to figure out the x value in the function that will produce what I want here. And since I want the natural log of 1.1, then I would say natural log of 0.1 plus 1, which means x is 0.1. So then we're going to take the 0.1 and plug it into our linearization. And since our linearization is x, we would say L of 0.1 is going to be 0.1. That's pretty straightforward. As a result of that, we can say f of 0.1 is approximately 0.1, which implies that the natural log of 1.01 is approximately 0.1. Okay, and so there is our answer. Now, if we were to check to see how close we are, just to double check to make sure this makes sense, natural log of 1.1 is 0.0953. Okay, so that's my approximation. The next part of this question says, is this estimate an over or an under approximation? Well, that's based on concavity. So how do I find concavity? I have to deal with the second derivative. So f of x was equal to 1 over x plus 1. And then I would, in order to take the second derivative, you could do the quotient rule. But before we do that, I like rewriting this as x plus 1 to the negative first. Because we know the chain rule, this is a little bit easier to take the derivative of than using the quotient rule. So we would say f double prime of x is going to be negative 1 times x plus 1 to the negative second, and then times 1 because of the chain rule. And we can therefore say f double prime of x is equal to -1 over x plus 1 squared. And so we ask ourselves, well, what is our second derivative? Well, in this case, no matter what number I plug in for x, the denominator is always going to be positive because I'm squaring, and the numerator has a negative value. So I can conclude that f double prime of x will always be less than 0 or always be negative. As a result of that, f is going to be a concave down function. And if we visualize this, if we have a concave down function, then the tangent line is going to be on top of it, which produces an over approximation. Okay, so that is our answer along with our justification there. Okay, now we knew this. We knew that it was going to be concave down because we're talking about a natural log function, and natural log always has well, I guess it's more like this. Natural log always has that curvature to it that makes it concave down. It's shifted back 1, but it's still concave down. Just to summarize here, we found our point by plugging in 0 to f of x. We found our derivative. We plugged in 0, and we found our slope of the tangent line. We created our tangent line, but we isolated y so that we could call it L of x, so it's a linearization function. And then we took 0.1 and plugged that into the linearization. We got 0.1 out in this case. And therefore, we could say f of 0.1 is approximately 0.1, which means the natural log of 1.1 is approximately 0.1. And again, because when I plug in 0.1, I get the natural log of 1.1. If I were to plug in 1.1, I would be finding the natural log of 2.1, and that's not what I was looking for. So the natural log of 1.1 is approximately 0.1. We take our second derivative, which we noticed is always going to be negative, and therefore the function's concave down. And since it's concave down, we're going to end up with an over approximation. All right, so that's a good example of linearization there. Now let's move on to a problem that I think is very important. It's not necessarily related to linearization, but it's something that you guys have been dealing with in regards to interpreting data points and interpreting information, okay? So it says, let G be a twice differentiable function with G prime of x less than 0 and G double prime of x less than 0 for all real numbers of x, such that G of 7 is 5 and G of 8 is 1. What is the possible values of G of 9? So if we were to look at this graphically, I don't think graphically is the best approach here, but if we were to look at it graphically, G of 7, 1, 2, 3, 4, 5, 6, 7, and then up 1, 2, 3, 4, 5. So that's G of 7. And then G of 8 is 1. So here's G of 8 is 1. Okay. We know those 2 points. The goal is to find possible values for G of 9. Well, G of 9 is going to be here when x equals 9. G of 9 is going to be on some y value on that dotted line there. So maybe I should draw a dotted line at x equals 9. Right? G of 9 has to be somewhere on that dotted line. Now, we don't know what it is, but we can take the information that we found here, or what was given here, and interpret that. So since we are trying to look for G of 9, this is the graph of G, we want to interpret what's given here according to the graph that we're talking about. In this case, we're talking about G. So we would say something like this. We would say since G prime is less than 0, we can conclude that G is decreasing. Well, if G is decreasing and G of 8 is 1, that would imply that G of 9 must be below 1. So I can conclude that. I could say, therefore, G of 9 must be less than G of 8. And so G of 9 must be less than 1. That's one thing I can say. G of 9 is going to be less than 1. Okay, this is a graphical approach now. Okay, now we look at the next part, and this is where it gets kind of dicey. This is where it gets kind of weird, because it says that G double prime of x is also negative. Well, what does that imply for G of x? Well, that would imply that G is concave down. And this is where it gets difficult to interpret according to the graph. Well, we can understand it this way, that if G double prime is negative, we got G is concave down. What if G of X, just hypothetically, what if G double prime of X was equal to 0 throughout the entire function? If G double prime of X was equal to 0, essentially what that means is that there's no concavity. Or if you were to take the antiderivative of this, we would end up with some constant value for G prime. We'd end up with some constant value for G prime, which would imply that G of X is going to be a linear function, if that makes sense. So we're taking the antiderivatives there. So if G double prime is 0, that means G is going to be some sort of linear function here. Okay, that's if G double prime is 0, but we know G double prime is less than 0, which means we have to have concavity, a negative concavity, so it's concave down, which means that the point G of 9, this point here, would have to be below this line, so it'd have to be down here somewhere. Okay, this is very difficult to see graphically. There's a lot of little things that we could do that would cause it to go wrong. So what I would recommend is, instead of looking at it in a graphical approach, I would look at it in a numeric approach. Instead, in other words, I would use a table. So if I were to create a table here of X and Y values, or in other words, G of X values, okay, we know that G of 7 is 5 and that G of 8 is 1. Now it tells us that G prime is negative, so let's go ahead and create a G prime graph, or G prime table. Okay, we know that G prime is negative, and we also know that G double prime is negative. So let's go ahead and interpret that. G prime of X is less than 0. So that means, okay, that's simple enough. Because we're looking at a table that has G prime values, we should be able to see that these values, these slopes, if you would, are negative values. But then if we look at G double prime of X being negative, what does that imply for G prime? And this is an easier way of interpreting it. If G double prime is less than 0, then G prime is decreasing. Well, G prime is decreasing. And you guys might be familiar with this problem. It has been on some quizzes or tests or things in the past. But since G prime is decreasing, if I can find one slope anywhere in this graph, I know that every slope after it must be less. So what I'm going to do is I'm going to go ahead and find the slope between 7 and 8. So I would say 1 minus 5 over 8 minus 7. Well, that's going to be negative 4 over 1, which is negative 4. So we would say that the average slope between 7 and 8 is negative 4. And by the mean value theorem, because G is twice differentiable, that means G is differentiable, and it must be continuous as well if it's differentiable. Since G is differentiable over the interval 7 to 8, that implies that the mean value theorem works, or we can apply the mean value theorem. Since the average slope between 7 and 8 is negative 4, that means G prime will be negative 4 for some value between 7 and 8, okay? Now, I want to know the value of G of X when X equals 9. Well, since the slope between 7 and 8 is negative 4, that would imply, because G prime is supposed to be decreasing, the slope between 8 and 9 must be what? Must be less than negative 4, because G prime is decreasing. So I'm going to just go ahead and arbitrarily put a value here. I'll call this Y. And if I were to find the slope between those, it would be Y minus 1 over 9 minus 8. Well, that slope between those two must be less than negative 4, because I need to see my slope, my G prime, decreasing. So I would say less than negative 4. And then solving this, we get Y minus 1 is less than negative 4, and then therefore Y has to be less than negative 3. So as long as this value is less than negative 3, the idea of G prime being negative, it's obviously going to be negative, and the idea of G double prime being negative will hold true. And we can test that. If I were to plug in -3 here, -3 minus 1 is -4, over 9 minus 8 is 1, -4 over 1 is -4. That doesn't work. But if I plug in a number that's less than -3, let's say -5, well, -5 minus 1 is -6 over 1. That's -6. The slope would be -6. That is, you see that G prime is decreasing from -4 to -6, and therefore G double prime would be negative. So basically, any value that is less than -3 for G of 9 will be valid. Okay. Now, with that said, let's see what I have here. So -4 will cause the slope to be, -3 would cause the slope to be -4. So plugging in -4 works, right? If I find the slope between those, I would get something less than -4. So any answer is valid that ensures that the derivative is getting smaller and smaller and smaller. All right, with that said, that wraps up our lesson. It was kind of short, talking about linearization and how to tell whether it's an over approximation or under approximation. And then I wanted to introduce, or not introduce, but go over a practice problem that I know that some students have been struggling with here. So if you have any questions, please comment below. Otherwise, I will talk to you all later.